Thank you very much for being here today. And Jonathan, the floor is yours. Thank you.
Thanks, Gabriel. Yeah, so I'm excited to be here today. The title of my talk is Microseismic Measurements, Ensuring Fracture Model Represents Reality. And my company that I work for is MicroSeismic Inc. We also have a number of different offerings within our company. The Frac RX is our oil and gas offering. We have CO2 Secure for monitoring CO2 injection and sequestration into the ground and the reservoir. Karst Alert for monitoring sinkholes, and then Microthermal Energy for monitoring geothermal reservoirs. Today, I'm going to be talking about geothermal. I have a good example, but also some we've done a lot of work in the oil and gas industry, so I'm going to share some results from that so that we hopefully we have some good takeaways for geothermal as well. So kind of an outline of what I'm going to talk about. First, go over acquisition methods, how we get the data, and then one of the most important things that we get from monitoring from the surface, we're primarily a surface monitoring company, are the focal mechanisms. This describes how the rock is breaking in the subsurface or at the hypocenter of the location of the event. Then we talk about a discrete fracture network model and how we calibrate that model. And then we can use that proppant model to inject proppant into the ground, into the fracture model itself to see how it's distributed. Talk about some fracture driven interactions and stress shadow effects. So how you change the stress influences where your fluid and proppant's going, and then how that all that information goes into an integrated dynamic model. And then we have a nice geothermal example. So our acquisition methods, we dominantly have two methods measuring or acquisition methods from the surface, and then one that can be used more downhole. The two surface methods are a frac star and then a buried array. Our frac star example is meant to be a less permanent installation that's laid out right at the surface with geophones emanating from the pad or the center of the wellbore that's being monitored. And then this can be laid out and collected very quickly. And then for more permanent installation, we have a buried array. These geophones are installed about 300 feet underground to minimize noise, cultural noise at the surface. And then we can also measure using a DAS interrogator, using fiber optic cable, and that can be done more downhole. Mostly what I'm going to be presenting on today is from monitoring from the surface for just microseismic event locations. And so, like I said, one of the biggest benefits from monitoring from the surface, actually, there's two really big ones. A big one is that we can monitor the entire treatment from toe to heel, and our uncertainty and event location accuracy is the same whether you're going from toe to heel or from shallow or deep. Unlike maybe downhole, where as you get further from your monitoring array, you have changing uncertainty and confidence in the locations. But also, when you monitor from the surface, you have a nice 2D footprint of your array, and you can fully detect the P wave radiation pattern. And that will give us an accurate representation of the beach ball for each of these events, which gives us the focal mechanism or that can be decomposed into the strike and dip of that fracture, as well as the rake or how that rock is moving. So the strike and dip is going to give you that fracture orientation. And then the rake is going to give you the movement along that fracture orientation. And I'm going to be primarily talking about dip slip versus strike slip mechanisms. And the two, the key difference here is the movement along that failure plane or the rake. And so in the dip slip case, the rake is in the direction of the dip, whereas in a strike slip case, the rake or the movement is in the direction of the strike of the fracture plane. So like I said, we detect that radiation pattern at the surface. So when the rock ruptures at the hypocenter location, some of the some of the energy would be going actually moving downward at the array, and some would be moving up. And so the location in between that would be the nodal plane. And so we detect that P wave radiation pattern, and that can be decomposed into these beach balls, which gives us the focal mechanism. A lot of times when you're treating a reservoir, the dominant fracture orientation or representation in a focal mechanism for just a hydraulic fracture is going to be these dip slip mechanisms, and this would be like in a normal stress regime. And then when we have different faults or fractures that are more oblique to the direction of SH max, they tend to be strike slips. So these dip slips tend to be more in the direction of SH max. So SH max would be at about an azimuth of 80 degrees. And then when we have different orientations of fractures or faults, they tend to be more strike slip in nature. And the nodal, there's always two different nodal planes that are equally viable solutions for any one of these beach balls. But the nodal plane that typically aligns with the event propagation orientation is going to be the dominant nodal plane that is active. And the auxiliary nodal plane in this one, you can't barely see it, but this one would be perpendicular to the propagation of the events, and that would just be the auxiliary plane. In this case, this would be the active plane that is most likely or is likely the failure plane for these events. And this shows an example of that P wave radiation pattern with a circular surface array with that represented beach ball. And you can very clearly see that our raw data P wave radiation pattern is consistent with our double couple solution. And a double couple solution means that we're really confining that to just pure double couple. We can also assume a more of a full moment solution. In this case, you can see this blue part of the radiation pattern doesn't actually come together right at a perfect crosshair, but actually the blue kind of extends through the red, which is more representative of a full moment solution, indicating that this event not only slips along a pure strike and slip plane, but also has an opening component to it, or a full moment solution. And like I said, all focal mechanisms have two potential failure planes. So one of the things we want to do is make sure we get the correct nodal plane. And one way we can do that is visually look at the event trend, but then we also have a fracture propagation analysis, or a lineament tool, where we are fitting planes to these events as they propagate in time and space. So as these events propagate and form a planar feature, we're fitting planes to that planar feature and mapping them on this plane here, or on this axis here. And we can see that in this example, they're primarily propagating in this kind of 80-degree direction, or 78-degree azimuth. And then when we look at the active nodal planes of the actual focal mechanism that we are calling the active nodal plane, they will typically align with how that fracture propagation analysis is detecting and fitting planes to those events. That way we know we've picked the correct nodal plane, and we can progress and make our discrete fracture network models and do our analysis in terms of stress inversion, et cetera, so that we know we've picked the correct nodal plane. And it's important to note that these 3D lineaments and the actual nodal planes can be quite complicated, as opposed to that previous example where they're primarily just going in one direction. This is showing fractures occurring in the Denver-Julesburg area, where we have fractures in all sorts of different directions. And so we get all sorts of different directions in our 3D lineament tool, as well as how we've picked those active nodal planes. In this case, we still see that our active nodal plane matches quite nicely with our 3D lineament tool. We're seeing all these different fracture orientations represented, even this other orientation here that's not as obvious. So we can test different examples. Like sometimes people think they might have pancake fractures, where the fractures are actually flat as opposed to these vertical fractures. And in that case, if that would be the case, we would see that in our 3D lineament and recognize, hey, yeah, maybe we are getting these pancake fractures. But far and away, mostly what we're measuring are more vertical oriented fractures. So then one thing that's important that it occurred back in 1976, this is a really seminal paper that I draw from, is that there was a lot of seismicity occurring in the Rocky Mountain Arsenal area. And it was due to injection or disposal wells. And there was strong correlation with the amount of injected fluid versus the actual number of earthquakes that they were detecting in the area. And they were able to relate the volume of the injected fluid to the sum of the seismic moment that was being injected. And that sum of the seismic moment was equal to the change in volume that was injected multiplied by the shear modulus or average rock property in the location, multiplied by this K value, which is some factor close to 1 that represents some scalar, or should represent kind of the detection threshold, if you will, or the percentage of the events that are actually measured through using that array. So we've carried that through into the way we model our fracture modeling, where we initially orient our fractures by the focal mechanism. So we get the strike and dip of those focal mechanisms. They're centered on the hypocenter. They are sized by the energy or the seismic moment, as well as using the rock rigidity or shear modulus of the rock at that location. But then we also calibrate our fracture model so that the total volume of our fracture model is going to be equal to the injected slurry volume minus any fluid that's leaking off from the formation, which can be measured from a DFIT test. And the reason that we do that is because we don't detect every single event. Some of the events are below our detection threshold, and we don't detect those. So we have to account for the fact that we are missing some of the population, and we need to scale up our fractures or enlarge them slightly to accommodate those missing events, that missing event population. Now our fracture volume, we know the footprint of it. We see the microseismic events. We know how it's oriented, whether it's, propagating to the east or to the west primarily, or going shallow or deep. And then we give it a physical meaning so that the volumes actually equal to in the injected slurry volume minus what's leaking off from the formation. And now we can inject proppant into these fractures on a stage by stage basis, guided by our fracture volume, so that we get a good estimate of where that proppant's going. And it's also important to note that our apertures, or the fracture opening, is also determined by the full moment tensor of the focal mechanism itself. And so for this example, we're showing this change in fracture volumetric percentage, or how much that fracture is opening. And we see that typically in a normal stress regime, the normal dip slip fractures that we see have the greatest amount of fracture opening. So those are going to be producing more of your fracture volume, whereas the strike slips tend to have quite a bit less fracture opening. And in fact, when you go to pure strike slip, they tend to be almost no opening of the fracture. They're just slipping along that fracture itself. So that's very important in how we are modeling these fractures and distributing that fracture volume. And so one example I want to give is when you treat a parent well and then have an area that's undergone depletion. So this has undergone production, and then you treat an offset child well. This depleted area can act as a pressure sink, and a lot of your fractures will go back towards that parent well if there's no pressure barrier in that area. And so this can be thought of as like two geothermal wells. Maybe you drill a shallow or a deeper injection well first, and you treat that one, and then the fractures are opened, and then later at a time later, you may drill your producing well and then try to treat that one in enhanced geothermal system. And if there is no pressure boundary, so you have removed the pressure from that parent well, your fractures can still go back to that original well. And if you're doing an enhanced geothermal system, you may not get effective new fractures, creating more surface area around your child well, and you may be just sending a lot of fluid and potentially proppant back to your original well that's being treated. So an example with microseismicity, we're looking in map view. We have a parent well here, excuse me, where we're looking in map view. This is a vertical well, so we're looking straight down that vertical well. And then we have two child wells drilled off to the east, and we're looking at microseismicity as we inject into the child well, and SH max is at an azimuth of about 80 degrees. So this stage is not really affected by the parent well. We have good symmetry around the child well, some interaction with child well B, and then we inject the next stage, and we see now as we're getting closer to that depleted region around the vertical well, we're seeing more energy going back towards that parent well. And as we get more in line with SH max, now more events are going back to that parent well. We also see a large increase in pressure observed on that parent well. And then subsequent stages that are close to that parent well, we see a lot of energy just going back into that parent well. So a lot of fluid and proppant going back to that parent well, not really getting as good of a stimulation as we would expect around our child well. And when we look at actually the how the treatment of these wells consisted of the treatment order, they're actually treating child well B, then going over to child well A, then B, then A, then B, then A. And what we see is we're actually pushing a lot of this energy even further towards the parent well. So we have to make sure that the treatment order is done in an appropriate way so that we're not artificially pushing fractures in a direction that we don't want them to go. And it may look like that we are sending a lot of, maybe even some fluid back towards child well B, but in this case, in this yellow shaded box, all these events have changed to strike slip mechanism. Over here, they were dip slip. And what that suggests is now we have an altered stress state occurring here, and we're reactivating fractures that occurred initially from child well B. And we're actually seeing that this area is already pressured up when you treat this other area. So that's what these strike slip mechanisms are telling us, that it's an altered stress state. That area has already been pressured up, and it's pushing our fluid and proppant away from that previously pressured up area. And the way that we would model this is we would have more fracture volume going in this direction than where we have these strike slip mechanisms. So the strike slips tend to have less fracture opening, so less volume created here, more volume created in this direction. And so what we do is we track those events per each stage. We're modeling them as an ellipsoid shape where it's modeled as a function of where that fracture volume is. So if it's elongated, like in that previous example, off to the west towards the parent well, each stage our proppant would also honor that fracture volume that's going over to the parent well, and we would fill out the fractures more towards that parent well. So what does this look like in reality? So we're taking the events from these about 8 wells. This is looking in map view. We have different, we take the focal mechanisms for each event. We create the fracture planes for each event. They're centered on that hypocenter. It's a fully calibrated model with the fracture volume. And then we can fill out those fractures with the proppant, so the actual proppant amount for each different stage that's being treated, honoring the orientation of how that fracture volume either is biased to the west or east. And so that this creates a fully dynamic model where our fracture model and our proppant modeling is fully dynamic with respect to how you change the pressure and the stress within the reservoir. And then we can then calculate enhanced permeability for each of these cells for this discrete fracture network volume. And the permeability is based on the number of fractures within these cells and the orientation of the fractures, as well as the apertures or how much that fracture is opening. And then we can get more to an enhanced permeability, and this can go into reservoir simulation. So another example, like when you have an injection well, and then a producing well on top, if you inject fluid into the injection well first and you create some fractures, maybe there's a lower pressure gradient upward and these fractures are growing upward, and you're monitoring with microseismicity and you detect these fractures, and then you say, okay, the fractures went up a certain amount, so now we want to go ahead at a later time and drill our producing well through here. Well, now when you inject into your producing wells, if you inject them together, sorry, I kind of got ahead of myself. If you inject and zipper frac these together, you'll have you'd be having areas where you have overlapping fractures, you have compounding pore pressures, you'll have stresses rotating in between them, and you'll get kind of some fractures that are separated by where you're injecting and going back and forth and creating these fractures. And there'll be some separation from these fractures. And on the second well that you're treating in the zipper, you'll tend to see more fractures from the compounding pore pressures, as well as you're going from toe to heel. As you go from toe to heel, you tend to compound pore pressures from the toe from each stage. Going back towards the heel, you tend to get even more fractures. And when you are injecting in map view from well 1 to well 2, this is showing your background SH maxes tends to be east-west, but in between the two stages being treated, we would see an apparent left lateral rotation as measured from traditional theoretical geomechanics. And so the reason that we get these stress shadow effects is that you're changing the stress and you're causing an increase that is, so this is kind of the center of your fracture. As you're moving away from your fractures, we see that you're increasing the stress more in the minimum horizontal stress than you are than the maximum horizontal stress, and more than you are on the vertical stress. So you cause both a rotation in the stress and a change in the stress magnitude. And so what you're doing is you're initially driving your Mohr circle to the left, causing failure. But in an altered stress state, you're rearranging some of these stresses. And that's why we would see a change in the stress state that we can measure, as well as the orientation of the stress. And so one of the things I'd like to do is to reference all our events to the stage center. This is nice to do, or stack all the stages on top of one another. If we do that, we can take all the microseismicity for each stage, stack it on top of one another, or reference it to the stage center. And this gives us kind of an overall picture of how that well was treated, giving us a plan to move forward as to how that volume would be distributed for future well development. And so if I do that, and stack all the stages on top of one another, and we look at the rake, or how the stress is changing, or how the rock is changing orientation for each of these different scenarios, we see that the stress shadow impact on neighboring wells can be time dependent on the stage lag time. So what we see is that if you treat a well in isolation, so all no other well treated in this area, that most of the fluid, in this case, the fluid is going to be represented by these virgin reservoir stress state events, or the dip slip mechanisms. So these cool colors, that's how your fluid would be kind of represented or moving. And the contour is showing how the proppant would be distributed. And then this is your kind of targeted interval, this white box focused in, and it's measured by your average well spacing and average stage spacing. So when you treat a well in isolation, most of your fluid and proppant is right around your stage interval, located in your target zone. And then when you have kind of this triple zipper effect, so you treat a well over here, treat another well on this side, about 650-foot spacing from the center well, and then treat the center well, we see these cool colors sandwiched in between these high colored areas. And so what it would suggest is your fluid and your proppant is sandwiched in between these outer wells and contained by these pressure boundaries. And so you can take advantage of these stress shadow effects and sandwich your fluid and your proppant in between these two wells. And then another example, so this one's now a cross-sectional view, looking in depth view. We treat a shallow well here, and then go in and treat a deeper well. Go in and treat a deeper well after about 18 days. So this shallow well is treated. There is a stress shadow effect that was here. Now it has gone away because this deeper well was treated 18 days later. And now all your fluid and proppant is going back to the previously treated well. And so you're not effectively taking advantage of a stress shadow effect that was here. And now you're just sending a lot of your fluid and proppant back to the shallow well. So this could be thought of as like if you treat these two geothermal wells, one that's shallow, one that's deeper. If the shallow one was treated first and then the deeper one was treated after that stress shadow effect has gone away, then you may just be sending a lot of fluid and proppant back to that previously treated well and not effectively creating as much surface area around the second well being treated. And so if we look at this example more in detail, so like I said, there's a well, initially offset wells over here, about 650-foot spacing. So they treated this well, then this other one, then within 0.2 days, they treated this third well. And we can see from these colors that there are changes in the stress. So the focal mechanism is going from this dip slip to strike slip, indicating that this area is undergoing altered stress state. And it's an area that where it's already increased stress, increased pore pressure, causing these pressure boundaries, so that the subsequent stage is sandwiched in between the two, and you get more effective location of your fluid and proppant in the area that's targeted. And like I said, we can take the different focal mechanisms. So I've taken focal mechanisms from this and inverted for the stress state, taken events from this location, inverted for that stress state, and this one inverted for this stress state. We see that in the more virgin reservoir stress state, where we have these cool colors, SH max is oriented about 80 degrees. That's consistent with wells treated in isolation from one another. And then when we have offset areas, we have rotations in the apparent SH max, like we would expect from theoretical geomechanics. And in this case, this apparent left lateral rotation tends to be more on the left side of the wellbore, whereas this apparent right lateral rotation tends to be on the right side of the wellbore. So you, depending on which side of the wellbore you're on, you cause these apparent rotations in SH max. And the phi, which is telling us about horizontal stress anisotropy in the virgin reservoir stress state, is typically going to be higher than it is in your altered stress state. So you're reducing this. So this distance is about 33% of the overall differential stress. So this would be shrinking as opposed to your virgin reservoir stress, as we would expect from theoretical geomechanics. And so this is kind of showing all the events. The dots are showing the events that occurred during this treatment of the center well. We see a lot of events occurring on these previously treated well bores. But like I said, where we get these normal mechanisms, so these cool colors, where you tend to have more volumetric or more opening of your fractures, you get higher fracture volume than you would in these strike slip scenarios. So you get less fracture volume in this altered stress state. So that translates to a lot less volume on your left lateral rotation and your right lateral rotation than you do in your virgin reservoir stress state, which are shown here in blue. And so when we carry that out to our total fracture volume that we've modeled, even though we have all these events occurring, a lot of them occurring on previously stimulated well bores, it turns out that the majority of the volume is actually where you have these dip slip mechanisms, and you're not creating a lot of volume with those strike slip mechanisms. So it goes into how we've modeled these fractures. And then when we inject proppant into that fracture volume, it also is guided by how that fracture volume is distributed. And that proppant is essentially forming the core of our fracture volume. And we see how that proppant would be distributed. So going back to this other example where you treat a shallow well, and then 18 days later, you go in and treat this deeper well, like I said, the stress shadow was around that shallower well, but once you treat this deeper well, now a lot of your fluid and proppant is just going back through the fractures that you've already created from the stimulation of the first well, and you're just not effectively creating a lot of fractures and fracture volume around the second well. So this has implications, like I said, if you have an injector well and then a producing well, if you treat the injector well first, and then look at that event cloud, microseismicity, you see that the fractures are kind of going up into this region, and you drill your second well to go through that cloud and complete it later, and then complete the second well, you'll most likely there won't be a stress shadow effect around that the first well being treated, and you'll send a lot of fluid and proppant just back to the previously treated well, not effectively creating more surface area around that second well. Whereas you could be if you're taking advantage of that pressure shadow effect. And so to overcome this, in the oil and gas industry, this can be thought of as kind of like a parent-child effect, whereas you drill a second well here, a child well, after this parent well has been drilled, completed, and under production, and you really don't want to send all your fluid and proppant back to the previously treated well. You'd rather create a pressure boundary around this first well being treated. So in this case, you could actually go back, repressurize this well when you treat the second well being treated. So you could repressurize this one and then get a better effective frac and more surface area around that second well. So it would act like a refrac. And the best way that in the oil and gas industry that they've done refracs is with these low rate, long duration pressurization steps, where they're keeping the injected pressure lower than your fracture closure pressure. Or this is where you start to create new fractures. So you don't want to create new fractures. You just want to pressurize the initial parent well, and then you increase the rate and pressure and create more fractures around that parent well. And what that does is it allows you to repressurize the entire lateral so that when you go in and refrac it, you get events that propagate from all the way from the heel all the way to the toe. If they don't do this repressurization step, they tend to just get microseismicity at the heel of the well because they've only just injected to hydraulically stimulate the entire lateral, and they just blow out the heel due to high pressure contrast from the heel to the toe. So if they do this long pressurization step, they can effectively repressurize the entire lateral, and then refrac the entire well. And then when they go in, this shows the difference between if you repressurize a refrac well and then go in and treat a child well, you have better containment on your events, so they're not all going back to the previous parent well. Whereas in this case, this was the parent well, not repressurized. They go in and stimulate the second well, and a lot of their energy is going back to the parent well. Whereas when they repressurize this parent well and then go in and treat this child well, they have better containment, less asymmetry, not all their energy going back to that parent well. So like I said, this can be thought of as two geothermal wells, one where you treat your injector well, and then at some time later you treat the second well. It may be advantageous to repressurize that initial well that was treated, so that you don't just have a lot of fluid going back to the well that was treated first. And what we see in oil and gas is, those offset child wells tend to underperform as compared to a typical type curve, whereas once you've repressurized the parent well, those child wells will now perform as well as the parent well. So now I want to show an example, a geothermal example. This is going to be not an enhanced geothermal system, but this is going to just be a traditional geothermal system. And the reason I'm going to show this one is because we have show rights for this, and we have publications for this so that we can show it. And this was the zone of interest that they were interested in seeing microseismicity. In this case, they have production well like this 1821, which is down in this area where we see this high area where we see microseismicity. And then this is their power plant. They have an injector well here, and this is where they have one of their producing wells. In this case, we are looking for a little bit different than just individual microseismic events, because they're just pumping fluid through a system that already is fractured, and we're trying to listen for fluid propagation through this geothermal system. So usually we use PSET to detect our events, which we're looking for a discrete event over a very short time interval. So just a single rupture of the fracture in an instant. Whereas when you're injecting through an entire system, and we want to listen where we have kind of repeated slippage of fractures in your fracture network due to increasing of this pore pressure, causing repeated slipping along the same fractures. So we listen for more weak repeated events in the whole geothermal system. And so the difference is we look for a longer time window. So we can use PSET to locate individual fractures, and then we can use our PSET where we open up our time window to listen for more repeated events that tell us where is the fractures located. So where they're causing more repeated fracturing due to the pumping. And so in this area, we see in map view, that the majority of the hot area is located along these faults. These faults are shown as black lines. Again, their pumping stations here, their injector well is here, one of their production well is here, shown here, 1821. Showing that the majority of the repeated events are in this fault-related enhanced geothermal system from the fault. And it's also consistent with the magnetotelluric volume, where we see more higher magnetotelluric values shown as these blue values. So that's where we're seeing the majority of the fluid being circulated. And then when we look in map view, you may even see another area over here where they could we're getting a lot of activity, which means that maybe they could even put another well in this location. So this is showing kind of where the injector well is. Here's the pumping station up here. This 1821 well is down here. And then here's their injector wells in blue, which would be about in here. So in this case, they use microseismicity to show primarily where a lot of their fluids are propagating through and coming back to their producing well. So you could maybe even think about putting another well even further deeper down into this region. And so in this case, we were monitoring for events from December 5th through December 11th of 2016. We saw events occurring in this magnitude region. And then right around this time period, we see a lot more events occurring and even much higher magnitude events. So as you go to more positive or less negative magnitude events, they become larger events. And this actually coincided with when they shut down their power plant. So what happened was they were pumping, we're listening to events, we're stacking energy over time, we're seeing those hot spots. But then when they shut down their pumping station, we see a lot more events, a lot higher magnitude events. And then, so this shows the event locations with respect to this fault. So this fault is actually running through here. Here's the power station. And this is around the same power station. These triangles are right around this pumping station. So these events actually popped off more northerly than their area of interest around their injectors and their producing wells. But they think that when they stop pumping, that the pore pressures then start to go back down, and a lot of these fractures start to close on themselves. And that's when we see a lot of these more discrete events. And then we can get focal mechanisms for the more discrete events. And you see them here. A lot of them are oriented north-south and in dip slip in nature. And they are aligning with these north-south faults. So a lot of the fractures are also north-south or more northeast, southwest that represent these other changes in faulting. And we can invert those mechanisms for the actual stress state. This is an example that I paired with US Geothermal, but they're showing their maximum SH max orientation. They've modeled it as being more north-south, with sigma 1 being vertical, so normal stress regime, with SH max being more north-south, and which is consistent with other measurements like world stress and other areas that they have more constrained data, where they also see SH max being north-south. So they've taken the focal mechanisms where the dip slips are also north-south. They're oriented in the same direction as local faulting, and when they invert for the stress, they're getting the same stress orientation direction. So kind of in conclusion, we can measure these stress shadow effects as they develop around previously treated stages and wells. And the stress shadow effects in my examples, they were from blue to red. The red areas is showing where you have elevated stress and potentially elevated pore pressure, showing you where you have increased pressure, showing where these stress shadow effects are occurring in time and space. And these virgin and altered stress states can be identified by performing the stress inversion of the focal mechanisms. And the regions identified as experiencing this altered stress states are also regions that are experiencing high stress and potentially high pore pressure, which would restrict your current slurry propagation into the area. And the areas that have that altered stress also have low dilation tendency, so they're not opening the fractures as much. And so after that pressure dissipates through the newly fractured network, new injected pressure fluid on offset wells can overcome the pressure from the because that pressure has now gone away, and now you just be sending a lot of fluid and proppant back to the previously treated well and stage. And so the regions identified as experiencing virgin reservoir stress represent initial fluid propagation into unpressured rock, where the fractures have the highest dilation tendency and fracture opening, and our modeled proppant can propagate through the DFN and is guided by that virgin stress state, where you have more of your injected fluid volume and creating more of your fracture volume. So I hope that gave you some insights as to what we do at MicroSeismic and Microthermal Energy, how we where we use all these events to create fracture networks and try to look at the stress and how that stress is dynamically changing, and how we can understand where fluid and proppant is moving through your reservoir.
Thank you very much, Jonathan, for a very detailed presentation. A lot of insights, a lot of questions were coming up, at least in my mind. But before we go to that, I'd like to go to a couple of questions that we got from our audience.
Absolutely.
Luis, I hope I pronounced that correctly, said, thank you, Jonathan. Presentation mostly focused on unconventional oil and gas experiences, obviously with an example on geothermal later, but what kind of analysis for an enhanced geothermal system can be made by your team when you're trying to quantify the enhanced permeability or fluid saturation from the initial natural conditions?
Yeah, so like I said, I'll just back up real quick. One of the things that we can see with the full moment tensor of our of the focal mechanisms is which fractures are dilating the most, or which ones are opening the most. They tend to be in the orientation of SH max. So as you have fractures that deviate from SH max, they tend to have less fracture aperture or more or less opening of the fracture, so that you're not going to be opening those fractures as much. And that goes into how we're calculating our enhanced permeability around that fracture network using our geocellular volume. So all of this information not only is the orientation of the fractures, but actually how much that fracture is opening goes into how we understand where we're creating more permeability than on other fracture sets.
Thank you for that. And just to follow up, I guess, you have a modeling workflow in place when you're working with these projects, but could you tell us a little bit about experience of validation? You know, whatever you were modeling and being able to validate some of those results in some kind of flow testing of these wells, or whether you're in verticals, and what's your experience with that?
Yeah, so like I showed where we had these parent-child effects,
Hmm.
in a lot of cases, we've monitored the parent well, and then we've modeled where those fractures would be, the extent of them, and then we've modeled where that proppant would be going to. And then later in time, we monitor a child well that's being treated, and we see a lot of events going back over to that parent well. And what it does is a lot of times it will illuminate the area that is depleted, and it'll concentrate in the area where you have more production and more depletion, which is areas that you have more of your proppant being located. And so we've had the luxury of monitoring both the parent frac and the child frac And when we look at where those depleted events are located, they're simultaneously located in the areas that we initially modeled where our fluid would be located, and they're even more concentrated around the areas where the proppant is located. We even have I have another workflow where we can see a lot of events occur very quickly right when you start injecting, and that's showing a lot of times where the fracture's collapsing on itself, where you have these open fractures due to proppant that may be shifting and closing very quickly due to actual depletion, and they coincide with how we've done modeling of the proppant as well. So that's one example of how we've done that testing.
That is pretty neat from a completion standpoint. It's like a completion engineer's dream, basically, come true. We'll move
Yeah.
on for additional questions. Louis also said something along the similar lines. It said, have you guys conducted microseismic monitoring for open loop geothermal or closed loop geothermal? If you have, what were some of the main lessons learned in some of these operations?
Yeah, so for the example that I was able to share with you guys, that most of the energy that we see, the hot spots, tend to be associated with major structural features like these faults. So where we're seeing these highs, that is where we also have really high permeability. So a lot of flow through that system. The and so and then where when we see more discrete events, they tend to be aligned with other faults in the area that can give us an idea of current stress state and virgin reservoir stress state in that area.
All right, thank you. We got a question that came in from Nestor Ruiz. It's a great presentation, Jonathan. One question about the tortuosity around the pipe or the hole. If you do a gun orientation in the direction of the fracture, then and then do the fracturing, and experience in that will improve the fracturing distance, decreasing the tortuosity around the perforations.
Yeah, so the tortuosity is an interesting phenomena. You and I'm thinking of tortuosity in terms of fracture flow. So you have preferential flow that would be in the direction of SH max, and then as your fractures are misoriented or less oriented with SH max, for example, as you're injecting proppant, your proppant would most likely fill more of the fractures that are in line with SH max, and any fracture that's misaligned with SH max, you have less proppant and less fluid going into those fractures, and we actually do take that into account in our proppant model. So fractures that are not as aligned with SH max or out of phase of SH max due to tortuosity effects would receive less proppant. And it also goes into our fracture modeling, where those more tortuous paths are also showing that we have less fracture opening of those fractures.
But on that same note, Jonathan, if we're thinking about secondary leak off systems, right? If you're in a, let's say, a natural fracture system, right, and you're generating a main fracture, but you're leaking off into the secondary system. Is this where your workflow and the DFN comes into play? Like, how do you work with the uncertainty analysis on that in terms of fluid distribution and essentially proppant slurry dehydration as you dealing with the fluid loss and distribution?
Yeah, that's a great question. So, typically, if the more defits that we can get, the better. So a defit will tell you how much fluid is leaking off into the formation. And so we like to have, if we're stimulating different levels, at least have different defits at different levels, if not different defits throughout the system. But then as you treat, go from stage to stage and from well to well, you're increasing your pore pressure, and you could think of it as you inject at one stage and you increase your pore pressure, so you're driving your Mohr circle to the left, you cause a fracture, and then when you go over to another stage or another well, and or even just your next stage, that area, the pore pressure is already elevated. So when you go to that next stage, it doesn't require as much pore pressure to drive your Mohr circle to the left. So that pore pressure is already elevated. You have less leak off into that system. So you're actually reducing the amount of leak off as you go from stage to stage and well to well being treated, and that can be accounted for in our modeling as well if we see that phenomena. So that's why you tend to get more microseismic energy out of the system as you go from stage to stage, or you're compounding pore pressure from well to well. You have less leak off to create more fractures.
Gotcha. Thank you for that. We have an additional question from Kanu, who says, when calculating your injection volume, how do you handle low magnitude events below your detection threshold that may be occurring during the stimulation? That's a great question.
Yeah, that's a great question. And so that's why we calibrate our fracture volume. We initially calculate just the volume of the fractures that we detected, and then we compare that volume to the total injected volume minus the leak off volume. And what we're expecting is that the total fracture volume that's being created should be equal to the injected volume minus any leak off into the formation. And what is always occurs when we do that comparison of what our fracture volume is from what we detected versus what it should be, it's always less than what it should be. And the reason is because there's a lot of microseismic energy that's below our detection threshold. So we don't detect every single event. And to account for that, we do this calibration step where we make our fractures a little bit bigger. They grow in the direction of the strike and dip of the focal mechanism, and they accommodate that missing population of events that is below our detection threshold. That must be accounted for in any good fracture simulation. Otherwise, we're missing a big chunk of the data there.
Absolutely. And one of the things I've heard in the industry is, those are micro events. They don't matter. I think generally comes from people that don't have a strong understanding of this domain. So I think it's important to keep that in mind. I would like to add another question, following Kanu's question. And earlier you showed the time of stop and injection, and there's a delta T between when events would occur. Uh, I find that very intriguing. So what's your experience been with other projects as well? Like, how is that delta T defined between, hey, I've stopped pumping, I have a certain volume I've injected into the rock, and now I'm seeing, microseismic events with a varying magnitude at a certain delta T between that. Like, I'm just a little more curious on that, based on your experience and expectations.
Yeah. So it can vary widely from formation to formation, and then how the whole system is treated. If you inject into a well and then keep that pressure there, and you could maybe potentially, and maybe even try to keep that pressure, whereas if you let the pressure and start producing from that well, that stress boundary can dissipate a lot quicker. Also, if you have natural fractures in the area, or if a number of wells have been treated and are connecting up, once you create that pressure barrier, it can dissipate through the local fracture network quite quickly. What I do is I track where these virgin reservoir stress events are located. And the reason I do that is when you treat a well in isolation, they tend to be right around the wellbore. If the wells are treated in rapid succession, they can also be where you're sandwiching with a pressure boundary on either side. You can retain those fractures close to the well. But then when in a scenario, sorry, in a scenario like this where you treat the shallow well and then 18 days later you go to this deeper well, now we're seeing these virgin reservoir stress state events that are cool colored going back to the previously treated well. So it indicates that there's no longer a stress boundary there, and your virgin reservoir stress state events are going away from the well that's being treated. And so in this way, I can try to get an idea of how long it takes for that stress shadow to go away and no longer be there anymore. And so it suggests that in this case, you really need to treat the shallow well and then get around to the deeper well quicker than at least this 18 days, typically less than about 10 days in this system, so that that stress boundary has not gone away. But
That's,
in a geothermal system, you could repressurize one well when you go in and treat the next well. It could be a system that needs to be investigated and see if you could create more surface area around the second well being treated.
yeah, I think that's a very interesting point. I think a big chunk of that is also the economics of the projects itself. One of the challenges in geothermal is that can't really copy paste the oil and gas economic model. So I'm just giving a very blunt example. If you're sitting out there and pumping for 2 weeks at a low rate and trying to repressurize the well that costs probably millions, it's going to be very important to have a very good justification for it, right? So it's I think it's a bit sensitive, but
Yeah.
it's important
It,
to
but
know
but then
why.
you are supercharging it with water that could be then produced from the other well. Um,
Absolutely.
it may be colder at that point than you wish, but you are charging it up with quite a bit of water and pressure. But
Yeah.
that's really good point taken.
Yeah. I will. I have a last question for you here. Something I was thinking of during your presentation. You've had a lot of experience in the oil and gas wells, and let's say in shale formations. When you're thinking about type of rock, right? You spoke about rock rigidity, and if you're looking at the shale world that you're, in, and then you're looking at granitic or, basaltic rocks, if you were to go into an EGS, how do you see that? How do you see the rock texture playing a role in the microseismicity world in terms of injection?
Yeah, that's a good question. In oil and gas, we tend to see most of the fractures being dictated by natural fractures. So the natural fractures play a big role in the orientation of the fractures, as well as the orientation of the stress state. They tend to be, you get, more fracture opening in the direction of SH max. But then with rigidity, as you get more brittle rock, you should have, it should crack better than less rigid rock. So if it cracks more apparently, then we should hear good acoustic emissions. So we should see a good microseismic energy.
Gotcha. Thank
And
you
the
very much.
10, yeah, absolutely.
You wanted to say something else? Sorry, I cut you off.
And higher rigidity may end up making higher magnitude events. So I
Mm.
don't know if the basalt, for example, is higher rigidity, but I'm assuming it's more brittle is what I'm thinking. I just don't have as much experience.
Yeah, if you were to look at the mechanical properties, depends how you look at it. There's some debates in the industry, but if you look at the mechanical Young's modulus versus Poisson's ratio, you're looking at pretty high numbers on the Young's modulus. So essentially,
Okay.
stiffer rocks themselves, but then the question is, what's the distribution? Is it homogeneous? Would you expect that to happen? What's the interaction with the natural fractures? I find that very interesting. I think it's definitely worth looking into it more.
Yes, absolutely.
Well, we have come to the end of today's presentation. I'd like to thank you for being here today. It was a very interesting one, and honestly, it's opened a lot of doors for future talks. Uh, a lot of questions that can come up. Almost, we could end up sitting here for a couple of hours and having discussions. So it'll be
Yeah.
important to think of what we can do in the future. I would like to thank the audience that was here today. Good questions. I hope you enjoyed the talk. Keep an eye out. The SP Geothermal technical section is going to organize a couple more events here in the coming weeks. We want to focus a little bit on well completion, casing materials, and connections. How do we deal that in the geothermal world? And we'll take it from there. I do see a question in the chat box about the recording. Absolutely, yes. Jonathan has been kind enough to approve that. So once this is uploaded to the cloud, I will be emailing the link to everyone. If you want to go over it again, it's got the contacts of Jonathan in the slides. If you want to get a hold of him with more questions and maybe interest in projects.
Yeah, and I encourage any of your listeners to email me directly or get in touch with me on LinkedIn. Feel free to contact me. I'm open to try to help you out and understand these things better.
Awesome. Thank you so much, Jonathan. Thank you, everybody, and have a great day, great evening.
Yeah, you as well. Take care.